he's already been in like 2 years into his work. Is this actually recording? Oh, yeah, okay. It finally showed that it was recording. I don't know exactly when it started. So my name is Theo de Campos, or Theo de Campos, whatever you find it easier. So I'm currently working for Vicon Motion Systems, but I'm actually on leave from the University of Brasilia, which is where I got a few students under my supervision, and Tiago is one of them. So today we have in the committee Krystian Mikolajczyk, who, I don't know, we don't even need to introduce him. He's one of the most cited computer vision researchers that I've ever met. And there is also, so he's from the Imperial College in London. And there is also Bruno Macchiavello, who is an expert on computer vision, or well, actually it's more on image processing, right? And at the University of Brasilia. And okay, so I'll pass the word to Tiago, who is going to share his screen and can start his presentation. So basically, he's going to talk for about, well, at most half an hour, and then we'll have some discussions led by Krystian and then Bruno, and then I can open it for questions from the public in general. And that will be it. I hope the whole section finishes in less than 2 hours, but that depends on our discussions. Right, Tiago, you can go ahead.
Okay, so good morning for everyone in Brazil, and good afternoon for Dr. Mikolajczyk and Albert in England. My name is Tiago de Carvalho Galo Pereira, and first of all, I'd like to thank you, Theo, for being my supervisor, and Dr. Mikolajczyk and Dr. Macchiavello for being here as a part of the examination board. Also, thank you, Tulio and Albert, and everyone else who is here to watch me presenting. So let's start. The title of our work here is No Labels, No Problem, Unsupervised Domain Adaptation for Real-World Person Identification. And we know that this title may sound a little bit ambitious, and we don't think that we have solved the real-world person identification problem. But the methods that we are going to present here actually can help anyone who is trying to deploy a person identification system in the real world, and can help to adapt their model for new cameras, new scenarios, new systems. And we think that even if we don't have solved the problem, we are actually helping anyone who has this problem. So first, let's define what is the passenger identification challenge. It's basically an image retrieval task where the objects in the image are people. So the idea here is that we have a CCTV camera that nowadays have everywhere, every shopping mall, airport, or even the grocery stores. Everyone has a CCTV system today. So the cameras of the CCTV system is always looking for people walking by your environment and are storing those images. So we have a person detection, a people detector. A lot of algorithms are ready for doing that, and we can crop just the part of the people in the image and store in a gallery. So here in the right side, we have the idea of a gallery. We can just like let our system gathering those images for about an hour, 2 hours. This problem is a short-term problem. So we are not able to re-identify people from one day to another, where a lot of changes can happen in the clothes, in the environment, in a lot of things. So it's a short-term challenge. And here we have a new person, this woman here, who walked by a camera of us, and we want to know where she has been in the last moments. So we can use these images as a carry and search her in our gallery. Here in the green rectangles, we have the example of other images where she appeared. And the idea of the person identification is to allow you to do that. And you can do an intelligence surveillance with this kind of technique. So the motivation for our work is because regardless of the scenario or the camera, the goal of person AG will always be the same. We want to match people from different no overlapping camera views. And here I say different no overlapping camera views because if we were working in a scenario with only one camera, there are multiple algorithms that are able to do that. Like we could do a tracking or other techniques that will just track the person in this simple camera. But when we are working with multiple cameras, we need to have a way to encode that person information and match it with other cameras. But the problem here is if we trained our model in a scenario with like these two cameras here, we will learn how the appearance of someone who passed through this camera will appear in the camera 2. But when we insert a new camera view in our system, the view of the people can vary. So here in the camera 1, camera 2, we can see that the person walked by the camera more like a side view of the person. Like this man is this one, this woman here is in those two images. But when we put this new camera, the position of the camera is looking more of a frontal view of the person. So as the pose of the people can change a lot when we add new cameras, the performance of our model will have a direct impact. And this can be a roadblock for a lot of applications in the real world. So we want to undermine this problem and have a way to unsupervised without the need of more human work. We want to enhance our performance in this new camera. So we can have a system that will adapt it for new cameras or new scenes. To achieve that, we set some auxiliary goals. So first of all, we implemented a baseline domain adaptation method to start from. Then we saw some flaws in this method and proposed a new backbone here to undermine these flaws. But the second method that we proposed have a little problems and was a little bit weak when we compared with state-of-the-art results. So we did a research of the state of the art and compared with this method here, and we saw flaws in our method and flaws in the state of the art. Then we proposed a new method who is comparable to the best algorithms in the world, and this is our final method. And while working towards these goals, we actually proposed some techniques that generated these publications. The first is domain adaptation for person identification on new unlabeled data. This was presented in VISAP 2020 last year, and we awarded the best student paper there. Because of this award, we were invited to do an extension of this work and publish in IJPray, where we just changed the backbone and we proved that using a more robust backbone with our method can enhance even more the results. So our method could be used with any backbone, and the better the backbone, the better would be the results. This extension is currently under review at IJPray. We are working to publish it there. And finally, our best method that we proposed further with undermining the flaws that we had before is the learn by guessing multi-step pseudo-label refinement for person identification. So talking a little bit about the background here to explain why we took the decisions that we took. First, we will discuss a little bit about some architectures. The problem in the person identification is that we want to identify the people. So the most important thing is encode the person information. We need to know who is this person, if it is in different poses, in different cameras, in different scenarios. So we want to always disregard the background information and use just the foreground of the person information to encode, to have an excellent encode of this person that will represent it in any camera. So as when we are working in a classification task, like, I don't know, ImageNet, we want to classify between animals, people, cars, airplanes, all this stuff. And to do a classification, we also have to disregard the background and just look for the object in the foreground. That's the information that we want. So we want to encode that foreground information and know what class it is from. So we thought that any architecture that was designed for the classification task would suit well for our problem here in the person identification. But in special, the ResNet is the best choice here, because when we are working with a person identification problem, we can have multiple semantic levels that will define someone, like the person can be male or can be a female, it can be tall or it can be short, maybe it has an object like a backpack or a cap, and these informations will be learned by our neural network in different layers. Like some simpler characters will be probably learned in shallower layers, and more complex information will be learned in the deeper layers. So as the residual networks have here these skip-through connections, we believe that it will ease the propagation of this information from multiple semantic levels to our final output vector. So we think that ResNet is the best architecture to start because of that. But we saw that the ResNet had a problem with its generalization capacity. So we started to look for another architectures that would solve this problem, and we find the aligned ReID++. The idea of the aligned ReID++ is that maybe two images of the same person are not aligned. So if in one camera the people walk by very near to the camera, their head will probably be up top in the image. And if in the other camera they are further away, their heads will be more in the middle of the image. So if we can just align the image, so we are always comparing head to head and chest to chest, legs to legs, it will ease our problem. But inserting a pose detection here or body parts detection here to do this alignment is too heavy. So the idea with the aligned ReID++ is do it automatically. So they also use the ResNet 50 as the backbone, and they extract their final feature map. And in this final feature map, we can think that the features that are up top here, their receptive fields when we propagate back to the original image would probably be around the upper part of the image. So these features here will be more in the upper part than the other to the middle, and that goes this way. So the idea of them is to propagate this final feature map for two branches. The first one, they will use their horizontal pooling to extract this information of the special, just like information from each stripe, horizontal stripe of the image. So they will have a lot of features that are local. The first one would be the up of the image, then the middle, and this go on. And with these local features, they use their DMLI algorithm to compare the distance between two images. In the next slide, we will enter in details of the DMLI algorithm, and they can calculate the local distance. Then in the other branch, they did traditional global pooling, where they have only one global feature that defines the person. Here, the any is the batch size. That's why we have multiple global features. And with this global feature, they use a softmax loss to do a classification learning while doing the metric learning, because this classification information that will classify people can help the final output vector to be more distributed in our vector space. So with the global feature, they can calculate a global distance using a traditional distance measure like an Euclidean distance or cosine distance. And then they do an average of local distance with global distance and use this distance to calculate the triplet loss. So here the MLI algorithm is dynamically matching local information, is the way that they found to do automatically the alignment in the image. So as I said, the horizontal features here will represent some horizontal stripes in the image, and they calculate this distance matrix from all the local features from one image to all the local features to the other image. And what we want here is compare all the stripes from this image with all the stripes from this image, and we want to find the shortest path from up top of this image to the bottom down of this image. So we have this distance matrix comparing all the local features, and we want to find the shortest path from 0, 0 to 7, 7 here. And that's what the dynamically matching local information algorithm do. So they create this distance matrix first, and then they find the shortest path that for this example would be something like that here. And the aligned distance have the distance of the sum of this distance matrix is in the shortest path, while the original distance will just comparing first with first, second with second, and will be the principal diagonal here. And that's the idea of the aligned VID++. But the problem with it is it enhanced the generalization capacity, but it was too heavy. And while we are working with domain adaptation, sometimes we want to create pseudo labels or compare all the images in our target domain. And using a heavy algorithm just like the DMLA wasn't feasible. So we couldn't keep using the aligned VID++ because of that. So we know that ResNet 50 lacks generalization and the aligned VID++ is too heavy to use. So we need to find a new solution. The idea here in the IBM net is to carefully integrated the instance normalization layers with the batch normalization layers, because the instance normalization can create representations that are more robust against the appearance. So here they will have information that are more robust against these camber variations, that we can have illumination difference, the color saturation can be different, but they can't just substitute the batch normalization for the instance normalization, because the batch normalization is very important for the discrimination against who is against the classes, against the person IDs. So they carefully integrate both of these type of layers in the first half of the deep neural network, and in the second half they just use the batch normalization. This way the weight of the IBM net 50 is the same of the classical ResNet, but they can increase the generalization capacity. So here we will talk a little bit about magic learning versus classification learning. In Person EID, we have an open set challenge. We have a closed set of person to learn from our training data, but when we want to deploy our person re-identification algorithm, anyone in the world can appear, and we want to be able to re-identify this person. As we know, the classification learning will try to learn boundaries here to define who is this class in our training data. So imagining this situation, we have 10 people in our training data, and we have these boundaries that will define here is this class 2, and here is class 3, and that go on. So when we have a new image outside of our training data for a new person, the feature will lay down somewhere here in our output space, but that doesn't mean that this person image represents someone from the class 9, because the class 9, these 10 classes was limited for the training data. So it not suit very well for the person identification problem. And then we have to use the magic learning, where we are like looking more to compact regions in our output space here. And if features from two images lay near each other in this region, we can say that's the same people. So we can see that new features that do not belong from anyone who was in the training will be in a new space here in our output vector. And if we see more than one image from this person, probably the other feature would lay near this one, and we could classify as a new person that wasn't the training data. Also, if we see another image from someone who was in the training data, we are still able to identify them, because they will just lay here inside the cluster of this person. So there is no problem when we use magic learning. And to apply the magic learning, we need the triplet loss. Actually, there is some losses that will guide our output space to a magic learning problem, but the triplet loss is the best of them, because the second best is the contrastive loss. That's our comparing pairs of features. And if the pair is from the same people, they just pull them together. And if it's from different people, they push them together. But the triplet loss will do this at the same time. So we have an anchor and have a positive example and a negative example. So our pulling together the positive pair and pushing away the negative example at the same time. So it enhances the result. But as the data sets have thousands of images, how we can choose these triplets? That's a challenge when we are working with the triplet loss. Based on the Herman's work, we found that batch hard is the best approach. And the idea of batch hard is inside a batch, we have a universe of comparisons of possible matches. And for each feature, we will choose it as an integer and calculate the distance for all other features that are from the same class. So P here is for positive examples. And we will choose as the positive example the one that is further away from our integer, and as the negative example, the one that's near the nearest one, because the nearest negative example is the hardest negative example, and the furthest positive example is the hardest positive example. So always working with the worst case scenario, we can achieve a better convergence. Here we'll just pass through the data sets that we used in our work, just to have an idea of what we're working with. The first one is the Viper that was released in 2007 and have only 1,200 images from 600 people. We can see that the number of samples is exactly double the number of identities. And that's a problem because we only have 2 samples per person. And another problem here is that they used just 2 cameras, but those cameras were not fixed. So every day they were in a new place and put the camera in a new place. So we have 2 cameras that was used, so just 2 devices, but a lot of different views. We don't have a clear pattern here. Then we have the CUHK dataset that was released in 2014. Now we have more than 28,000 samples, very better to use our deep neural networks. We have more samples. And they say they used just 2 cameras, but actually this was in the Hong Kong University. They used up to 6 surveillance cameras, but for all the person ID, they just said this person appeared in the camera 1 and then appeared in the camera 2, but this camera ID didn't mean anything. Just this camera is different of this camera for this person, but we do not have information from all the 6 cameras to really learn how these 1 to 6 looks like and 2 to 3. So it's a challenge here too because of that. And this is the only indoor dataset that we work. Then we have the market 1501. This name is because they have 1501 identities with more than 30,000 samples. And this is a great data set because they used 6 fixed cameras in a local park. And these cameras could capture some person in all the 6 views. So we have examples of the same person in all the 6 views, and it's very easier to learn from it. Then we have the Duke MTMC dataset that was released 1 year ago. Also a lot of images, a lot of people. They have 8 cameras. They do not have the same characteristics of the market, where we have an example of the same person in all the camera views, but they have examples of all camera pairs. So maybe for one person, they have examples 1 to 2, 1 to 3, 1 to 4, and the other person 2 to 3, 2 to 4. So in the totality of the data set, we could have examples of all the pairs of cameras, so there is no problem. And here is a table of the null. So we start with our first method here, the GAN plus pseudo-labels method. We had a general training strategy that we used to all the experiments in this method. So we used the ResNet50 and the aligned VID++ as the backbone, the triplet loss with batch hard, and the Adam optimizer. We also proposed here a batch scheduler algorithm. That's because of the idea of the triplet loss. As a triplet loss with batch hard will select the hardest example inside the batch, the size of the batch will directly impact in the complexity of the problem, because the size of the batch is the universe of comparison that we have to choose the hardest samples. So if we have a smaller batch, it will be an easier problem, and for a greater batch, it will be a more complex problem. So the idea here is start with a smaller batch, and as the model starts to converge in this smaller batch, we increase the batch size, and this way we keep increasing the problem complexity little by little and allow our network to have a good convergence without starting with a high complexity problem. Then our first step for the domain adaptation is using an cyclogram. The cyclogram here allow us to adapt the style of the source domain image to the target domain image. So we train a cyclogram between the source and target domains, and we will just transfer the style from all images from source domain to the target domain style and leverage the labels that we had in the source image. So this way we generate an intermediate data set that have the source domain labels and have a style more closer to the target domain style. Then we fine-tuning the neural network we previously trained in our source domain in this intermediate data set, and we expect better results because we have a style closer to the target style. Then we have the pseudo labels step. The idea here is we actually want to learn what are the characters in the target domain. So we want to really look for the image in the target domain. So we use the previously trained neural network that was trained in the GAN intermediate data set and extract features from all the images in the target domain. So we have something like that, a lot of images, a lot of feature vectors, and we have to cluster these images. So we use k-means clustering to create the labels here, and in these clusters, each cluster will be defined as a password ID. So we generate a target domain dataset with new labels that were defined by our k-means, and we fine-tuned our previous network in these pseudo labels. So for our results here, the baseline is the ResNet 50 result. And as we can see here that almost in all the cases, the cyclogram is better than direct transfer and the pseudo labels is better than cyclogram. Here, direct transfer stands for when we get the network that we trained just in our source domain and direct apply it in the target domain. This way we can know how our generalization capacities are, because we don't have adapted nothing of our network and direct applied it. And it's also interesting to notice here that when we use the COHK, we have the biggest jumps in accuracy. So we can see here Viper to COHK 5.9 to 31.9, here 26 to 37, and that happened because the COHK was the only indoor data set, so we have a lot of texture change when we applied the GAN. And in the other cases where the Market and Viper were both outdoor, the changes were more in the color space. So we see here that the texture change applied by the GAN is more important than just color space changes. And here we have the aligned VID++, and this is just to prove that when we use a better backbone, we can achieve better results. And this happens in almost all the cases. The only one that doesn't happen that is Viper to COHK, that here was 36.1 and then 20.4. We believe that's because the aligned VID++ is a little bit deeper and it has the local features that it wants to learn. And as the Viper had only 1200 images, it wasn't enough to learn well the aligned VID++. But this previous method has some problems. And when we look at to the state of the art, there were a lot of problems. So we want to undermine all these problems and create a method that will be comparable to the state of the art. So the first one is this lack of generalization. The aligned with D++ helped, but it was too heavy, and we couldn't use the DMLI in the pseudo label generation. So we need something lighter here. So the idea is to use the IBM net to solve this. Our pseudo labels was noisy and it had low quality, and we believed that we were generating the pseudo labels and that's it. But now we've thought, if I generate the pseudo labels and train my neural network in these pseudo labels, now I have a neural network that is better in my target domain. Why I don't generate pseudo labels again? Probably they would be better, and do that as an iterative process to keep improving my performance. Also, the cameras, each camera has its own characteristics, and this was dominating the pseudo labels. As all the cameras from the target domain are new cameras, this information was very difficult to be disregarded, and the clusters generated by the pseudo label tends to cluster more images from the same camera than images from the same people in different cameras. So this was a problem. Also, the high computational cost of the GANs, we couldn't generate a very good intermediate data set because we didn't have machine power to do that with GAN. So the steps of our multi-step method, the first one, our training strategy, as I said, the IBM Net 50, the semi-adult optimizer. Now our loss is not only the triplet, we have a three-factor loss function here, where we have the triplet loss that will guide our metric, but we also use an ID loss. We choose to use the label smooth version of the cross entropy because the ID classification is not our final goal, as we have an open set problem. So we don't want to have a hard example of the classification here. And we also use the center loss that will regularize our clusters in the output space when they were too sparse, because we want to have compactness clusters. This is the learning rate scheduler that we use it for 9 training epochs. Our second step is the progressive learning, is the idea that I said of doing iterative process of recreating the pseudo labels and retraining our network in the new pseudo labels. So we have the model train the source domain, generate the pseudo labels, then fine tuning on these pseudo labels, back to the generation, fine tuning, and we keep cycling this until the full convergence. Here, for the clustering technique, the method before we used the k-means clustering that have a problem, because the k-means will use all the features that are in our space to generate the clusters. And some features are outliers. And these outliers will just put our clusters in a position that not very interested, and it's not the ideal. As we are training the pseudo labels, we are just generating compact clusters. So if you use all the features, it will just tend to generate the same pseudo labels in the next step, because we are just learning with it. So the DB-scan with its outlier detection, it's very better because we can just consider these outliers, do a very good job for the clusters that we generated, and in the next step, maybe this outlier will just lay near a cluster and belong to a person, and we can use in further steps. Also, we use a cluster selection because as we generate our sample, we use a PK sampler. The idea of the PK sampler is select P identities with K samples per identity to generate a batch. So if we have a P of 10 identities and a K of 4 image examples per identity, we will have a batch size of 40 images. So if some of the clusters that will represent a person ID have less than K samples, it will not suit each will not suit for our batch creation. So we just discard this cluster and don't use these features. The same happens for the camera features. Our features from same camera, we want to learn how someone looks in a new camera. So if all the examples I have for a person ID is from the same camera, that's not interest for me. So I don't use this cluster and let these features for the next step of clustering. Then we do a camera guide feature normalization. As the camera characteristics was dominating the cluster selection, we have to normalize them. As here in this image, the shapes represent the camera IDs and the colors represent the person IDs. And we can see that the features were much more clustered by the camera information than the person information. So we grouped the image from all the features from all the cameras and did just a simple normalization here. And we have an output space that's very, that will help us to cluster better. Our final unsupervised domain adaptation method is this cycle here, where we train our model first in the source domain, then we apply it in the unlabeled target domains to extract their features, normalize with the camera-based technique, then do a clustering with outlier removal, the clustering selection, and create our pseudo labels, fine-tune our model, and we keep cycling this as the progressive learning recommends until the full convergence. And here we have our results. Now we can compare our results with the state-of-the-art methods. And we can see that our final method, when used alongside with re-ranking, achieve the best CMC rank run results and mean average precision results in both cases. We can see here that MMT have very good results, very near 2 hours. We think that their method actually, we know that their method use 2 CNNs in a teacher-student manner, and it was a really heavy method. Probably if we could use a heavier method, we would have results better than theirs. That's why. But with our light method, we have an excellent result. And here where the Duke is the target domain, we have the best results in all the cases. And that happened because of our camera normalization technique, because Duke have 8 cameras, so the camera variance is too high here, and our camera normalization is the key to achieve good results in this setup. So in this work, we proposed 2 methods for domain adaptation in password ID. First, our GAN plus pseudo labels that was used with the ResNet, and we proved that it can be better if we enhance our backbone with the aligned VID++. Then we have our multi-step pseudo label refinement, where we solved a lot of problems and achieved a state-of-the-art. With that, we believe that our main research goal was reached, but we know that there is some improvement to be made in the manuscript, and also some experiments that we can do to strengthen our arguments. So we propose this schedule here to enhance our manuscript and finalize these masters. Here we want to first improve the manuscript with our orientations, then perform these additional experiments, revise the final thesis, and prepare the presentation. That's all. Thank you.
Okay, thank you. You were a bit more relaxed than when you practiced and ended up running over time a little bit, but I think it flew better than before. Anyway, sorry. So let's crack on. I'll just ask Krystian to make comments and ask questions. I guess you can do in whichever way you want, if you want to iteratively or bombard him with questions, whatever you want.
Right, thank you. Yeah, first, let me just start by saying that, I really enjoyed reading your thesis. So the report was really good, especially, from the beginning, you introduced the problem very nicely, and then review the background, also give some definitions of different terms that are specific for this domain. So that's really good. And also nice that you don't go too into textbook knowledge, which quite often happens actually in those reports, that people try to explain how neural networks work or how those basic tools work, which is not the place for it. So all that is really nicely done, and also obviously congratulations on your paper, and then the best paper award as well, right? So that's a really good achievement. Yeah, especially at at master level. So that's well done. So I have some questions and suggestions for continuation of your experiments, so you can maybe improve and explain a little bit better in terms of why you get the results that you get. So first, going to your title, okay, when you say no label, no problem, all right, so that's the problem is that actually you do use labels and quite a lot, right? So that's not exactly this type of unsupervised learning that you are doing, where you can get away without using any labels, especially that you are using pre-trained models in source domains where actually the labels are needed. Okay, so that's one thing. So it's not completely unsupervised, but yeah, that's just that's minor, really minor thing. So then you actually showed one scenario at the beginning on the slides. Yeah, this new camera. So all your test experiments that you were doing, you did transfer from data to data, right? But you
Yes.
could just try to transfer for one camera and see, how this specific scenario works. Is it better? Is it, easier problem? Because we can assume maybe the cameras were more or less the same. The season of the year was the same, maybe, that they were collecting, right? So there is less changes than what you observe when you go from one type of the data, like Duke to market. Do you think that's the case or not?
Yes, I think that's something that guided us to do the data set change is because we always want to compare our results with other researchers, and everyone just is trying to adapt it from one to another. But sure, a new camera would be a very easier problem than a data set change. Actually, I have done this in the real world for my work. We just deployed a passenger identification system there, and sometimes we had to add a new camera, and we had some work to there. We annotated the data, so we used labels, but the adaptation was very faster than the first one when we have to learn this scenario and the environment. So sure, just inserting a new camera in the same environment is an easier task than adapting to a totally new.
Yeah.
Just to clarify, Tiago is actually a part-time student, and he's at the moment, he's been working for a company called Cyber Labs, and some of the work he did had to do with surveillance cameras and stuff. So yeah.
So you have a practical experience in actually
Yeah.
deploying systems in a real application. No, that's excellent. I think that's a really good experience. So I think this is true that sometimes a little bit of real data annotated just does miracles compared to all those domain transfer things. So that's the definitely what I see that this is what you found out as well in your real application. I think this would be as a baseline or something, for completeness, would be interesting to see how much easier is the problem in terms of transfer, because very often the pose, you would have to choose the camera that has very different pose. I don't know if you noticed in those ReAD data sets, there is a significant bias from the poses. So all the systems, they are aware of it and kind of try to counter it, but it's very often that the systems bring up in the rankings images that have the same pose, right, rather than actually the same ID from different pose. So that's that's one of the still big issues. So your proposed method was to do the clustering and to do pseudo labeling, right? So you rely on pseudo labeling a lot. But what I didn't find actually in your experiments is to measure a bit, how good this pseudo labeling is, because I don't know how much noise you end up with all those steps and decisions that you make, what clusters to use, how big, and so on. How good eventually is the data that you are getting for training, especially in case of this second technique that you are using, where you are improving the results over the same source training testing. So this is this is quite surprising, and it would need really much more explanation in terms of extra experiments to show what kind of noise you are injecting in the model that it actually gets better than the original one. So did you notice that, or did you think about it?
This idea of measuring how good are the pseudo labels. I think the first experiment that we did it was before the GAN plus pseudo labels method, or maybe the first time we tried it, we tried to measure that, and it was really noisy. I think that like 5% of the clusters were correct, and all the others have too much noisy. So, but it would certainly be very interesting to know that in our newer method, which had a lot of things to enhance the cluster quality.
But you see, if you had these results, this is always very important to include in the report. I mean, it's not gonna make your method look bad. It's just, it gives more complete picture, you know, what
Sure.
it is really that is going into the method. Because at the moment, if you measure just by looking at the final performance, right, there is a lot of things that are going on in the whole method. And there are a lot of steps, and we don't know, you know, whether the actual model is benefiting from this noise, or the data is actually that clean, or what is really going on there, right? So that would be very interesting to see those clusters, especially in this case of the agglomerative clustering, where how clean those are if you select, you know, that big clusters, and what's the percentage of you know, correct labels there, how many clusters do you have, how many IDs you cover, how many outliers are. It's this sort of proportions, percentages are, I think, quite useful. Yeah,
Sure.
and if you are extending this to a journal, then definitely this is, you know, something that I would imagine would come back as a suggestion to do.
Yes, I will definitely do that.
So another thing, because you made a sort of fairly clear distinction between metric learning and classification learning. So do you still feel there is that, because that used to be in classical machine learning, that you know, we were doing either really pure metric learning for distance calculations or classifiers, but these days when we have, you know, so many nonlinear sort of methods and layers, fully connected layers, which are really kind of nonlinear projections, do you think it's still the case? Because I would say that there is actually a lot of both going on in every method.
Actually, I'm not entirely sure about that. Before, I really believed that there was a distinct difference between classification and metric learning. Then I started to look for some face recognition papers, because in the face recognition data sets, they already achieved like millions of samples of thousands and thousands of people. And the idea of choosing triplets, as we said in the batch charge, is even more complex, because to compare all people against all people and do this push-pull iteration would just take a lot of time. So the idea that they had there with the, I think is ArcFace paper, they used a classification learning loss. It was a softmax loss with cross entropy, and they added the margin from the triplet loss and from the metric learning algorithms inside the cross entropy with softmax, and that helped them to, in every batch and every example, just a little bit compare this ID to all the other IDs in the dataset, because they have this softmax with cross entropy and the margin inside it to guide for more of a metric learning problem, their classification learning problem. So I think that there is some gray area there where they blend and they kind of work well together, and there is a lot of things to explore in this area.
Yes, yeah, I definitely agree. I mean, I examined the Jiankang thesis, so that's the guy that did the ArcFace last year, and their modification was actually not that significant in terms of formula compared to prior work. It was really on the level of how you calculate the margin, and the results, the performance, was surprisingly sort of improved. So those tiny things quite often make significant difference, and it's difficult to say whether it happens in the better metric learning or you know, sort of more in the classification part. So that's the but what's I think, going back to your results, what's your guess in terms of those results on this comparing supervised case and your unsupervised training, where the performance is actually almost the same when you go from market to Duke or Duke to market. What's the reason? I mean, if you're saying that it is noisy the way you obtain the labels, how come the performance is the same as in a clean case?
That's a very good question. I think that there is a lot of research nowadays trying to discuss if the ImageNet initialization is actually the best method for any task that you are working for, because ImageNet have a lot of examples from, I don't know, cars or planes and open space, trees, animals. Does it really learned some good visual representations for our problem here in the passenger identification? And when we are working with the fully supervised method, we always start from the ImageNet and then we do a transfer learning our passenger AG dataset and achieve those results. But when we have our method here that we already forgot the information from ImageNet that were not important for the passenger AD problem and started with some weights from a previous domain that's working with the same task that we are working here in our target domain, that people, that's passenger AG, I believe that the visual representations from the initial weight when we start our domain adaptation methods may suit better our problem than the ImageNet weights. So maybe we are starting from an upper point with our domain adaptation technique here, and that's why we can go further to get better results. To try to prove this argument, we are thinking about changing our upper bound experiment. Instead of using direct the supervised learning in one data set, we are thinking to merge Duke and market and do a supervised learning with the merged data set. So we have the 14 cameras and the information of the two of them together to have a new upper bound that we believe that suit better for our problem than something that started from the ImageNet. I think maybe there is something in there.
Yeah, I think mixing the data sets and trying to do this experiment is definitely interesting. Yeah, that will probably give some indication. It's hard to predict in terms of results. I mean, people don't usually mix the domains to improve the results. That typically goes lower, a bit lower on both domains than just sticking to one. But it will definitely be interesting to have this as extra result. Yeah.
Yeah, just a comment. I think Tiago gave a very good answer, but his text and the results that don't actually give an answer, because I mean we like I don't think you're actually presenting results without semi-supervision, or are you this table? I mean, whatever you call ours is already doing the iterative training with label propagation and all of that. So yeah, in fact, showing what's the actual baseline without the pseudo labels is not at least it's not in this table, right? It might be in the thesis, maybe.
This table here, we have the supervised results, the direct transfer, and the pseudo label strategy in the third line.
Okay, yeah, that's better.
Yeah, so one more line, the mixed, I think, data set will be interesting, right, as well. So that's since you are there, actually, because the second best or third best is MMT, right? It is already also based on pseudo labels. So did you say that it's heavy in terms of complexity, or what's different what they do?
They were using pseudo labels, and they have two neural networks that were learning together, and one was generating pseudo labels to the other. So if they had like a different, I don't know, path of learning, path of knowledge, that they are getting pseudo labels that will be more, I don't know, impactant, that will generate a major impact in the other network that's learning from different sources. So the idea is to train two together and one is teaching the other. That's why I said the teacher-student setup.
Okay.
It's an idea of two together, one teach the other.
Okay, yeah, so that's also quite good idea. And then also in this early experiments that you did in terms of style transfer, right? I also found the examples that you were showing quite good actually. So the transfer really looked like working well, because yeah, exactly. You could, if you directly compare the transferred images, they seem to be fairly close, right, to the other domain. So that's not. But did you try to measure a little bit more quantitatively what really happens in those images? Because you at the end you give some analysis that there is some color transfer, some intensity, something. But this is by looking at the images, right?
Yes.
Did you try to or think of a metric that could quantify a little bit more what is changing there, what kind of things happens, what sort of color transfer happens?
No, actually, I didn't find any metric to measure that in the time I did this experiment, and I think maybe there is a flaw here because I think in the thesis I should show more examples and show the negative examples too. As we presented this at VISAP and we wanted to show just the best examples, this is the image that you generated there, but looking for all the images in the data set and the intermediate data set that we generated, there were people who lost their head or lost their arm, and we have some morphological problems in the transfer where the people didn't maintain their real appearance. So I think that I can enhance this discussion with the negative examples too.
Yeah, no, I agree. This is, I would say, because we also tried the GANs for generating data, and the quality of the results were nowhere close to this, right? So exactly, there were a lot of noise, extra noise. Especially we tried different poses, so maybe it's a bit more difficult. But still, I think then the noise was, yeah, you could see that it's messing up a lot in the images. Yeah, so definitely adding some fail cases will be good.
It's I mean, there are several newer works on style transfer, right? And like you can regularize in a way that you don't actually deform your objects. So this like losing head is something that shouldn't happen if you use the right hyperparameters and train it properly. But I find that, in general, the texture transfer happens. I mean, it tends to work, but whether this actually helps with your final goal of doing person re-identification, that's a completely different question. And I believe, well, I mean, my recent findings is that actually doesn't help that much. But yeah, anyway. It looks so yeah, like style transfer has evolved a lot, and when you look at the recent papers, they seem to focus on deforming more than what you would want for this kind of application, like converting people to anime characters and things like that. But if you actually what you want is to do domain adaptation, maybe that's really not the best. It's probably better to use some better normalization strategy and things like that. Anyway, sorry to interrupt.
Since you mentioned the normalization, you used camera normalization, right? Camera guided normalization for your method, but the results that you used for the supervised case, did you also use camera normalization?
No.
Okay, so do you know if that would improve or decrease the results?
Actually, the first idea of the camera normalization we saw in supervised work, where they substituted the batch normalization layers during the training for camera batch normalization layer. And they were normalizing by camera during the training in the just in source domain and then validating source domain, and they presented some quality results. I don't remember if it was better than our supervised result. I would have to check, but we didn't use.
Yeah, so you see, if you are doing too many things in your method, then it's very hard to identify, where the improvements come from. So you need to break it down into, some individual components that you are adding to the baseline. So I think if you are comparing, your part, then the baseline should have everything else. Okay, like the camera normalization and yeah. So that would at least expose really where the benefits are coming from. Okay. So also you mentioned the backbone, right? So you said that the ResNet, okay, was weak, and then the aligned was too heavy. But there are other baselines, because then eventually used IBN, right? So did you try like PCB or something like that? Because a lot of people are using this as a good baseline.
No, I saw them, but I haven't tried.
Because I think it's not too big in terms of the network to train. It's at least yeah, from what I know, and it gives good results. And I think it's better than just using some sort of general feature generation network. So that's also worth trying. Okay. I don't think I have any more questions. So yeah, if Bruno wants to add anything, or please go ahead.
Thanks a lot, Krystian. We can get back to you if, feel free to ask more questions. We don't need to follow the very rigid structure. But anyway, so Bruno, this is your turn.
Okay.
Feel free. Yeah.
First, thanks for the invitation. As Krystian said, I really enjoyed the text. I think it was well written. There are some minor things that I think they need to. Sometimes you make some affirmations that are not right. But the text is very well done, right? I really enjoy the work. I think you guys, you, Tiago, you have proved that this is a master thesis. I think this could be the final thesis. I think you really could.
Thank you.
Right? You have the publications, right? Is well done for what I expect for a master's student, right? So I want to say that up front. But Krystian does mention, some key elements, which is what I'm gonna, try to contribute, right? So what I missing when I read your thesis is exactly what did we learn, right? Because your problem is complex, right? And you are not focusing in one thing, right? So Krystian mentioned the fact that noise is helping, right? That cannot happen because it's not helping. It has information. If it has information, it's not noise. Right?
Yes.
Right? But when I read that, I think this may actually make sense, because what you're doing first, I kind of love the title, because in my field we never do this kind of titles, right? Cool title.
I don't think we should keep this title anyway, but he insisted, and I let. Yeah, I just
like
my thought was just, well, let's see how it goes in the Viva, you know.
Yeah, but I kind of like, right? Anyway, in my field we use these boring titles, but I agree with Krystian that you're actually using labels quite a bit, right?
Yes.
So the title is misleading, right? But what happened is that you're doing transfer domain, right? You're doing these pseudo labels, and you're doing a loss that measures, run examples, difficult run examples, difficult write examples, and the ID. But I kind of sat and analyzed the problem and went through, quickly. I didn't actually do it, right? But I went quickly to the math, right?
Yes.
So the backpropagation algorithm, right? The gradient. What's going to happen at some point is that you reach a direction, right? The gradient is going into a direction, and that direction is defining what is a bad example, what is a good example. So in a point, your training itself is kind of proving itself because it's a closed loop, right?
Sure.
So when I expect, okay, this is not good. This is not optimizing the solution, right? So when this noise help, I think, okay, that makes sense because this helps break that loop, right? But it's not actual noise. That's not the truth. It's because those samples are giving you information, new information.
Yes.
Right? So what I think, right, again, I think your work is, for me, for what I spent for my thesis, I'm completely satisfied, right? But we are here to try to make it better, right?
Sure.
So what I think is missing is, like, you decided what problem are you trying to solve, right? So you're solving a generic problem, and this re-identification is a case study, right? Then what I think you need to study is a metric, as Krystian says, a metric of label, how these labels improve your training, and it has to be in this metric. It doesn't have to depend on the loss. It has to be similar to active learning. That's something that they keep coming back to my mind. Why you are not using active learning? When I evaluate if a new sample is giving me more information or not, right?
Uh-huh.
So if you're trying to solve a generic problem in this person identification is just a case study, that's the answers I think you need to focus, right? Or not, then you're actually focusing on a specific problem, right? Then I think you try to do too much, right? If you're focusing on a specific problem, then your signals have some characteristics. There are some features, right, that you need to exploit, right? And you're trying to do a little too much, and that's why I had that feeling of some things work because they work, right?
Yes.
Because you try a lot of experiments and they work. Right? But I didn't learn anything from it. Right?
Yeah, I got it.
Right. So I think that's what I think I in the end that's what I got. So the fact that noise is helping makes sense because the chapter 4, like I said, is a suboptimal solution. Once the network converges, where the gradient is going what direction, you are actually helping it to keep it there, right? So the noise makes sense that it helps. But it doesn't make sense that it's actually noise. It's not noise. Right? So that's the idea. You are trying to solve a more open problem. Then I need to see a more theoretical background, right? I need to see a more a study that help me evaluate what the amount of information these labels are given, right? And but if you are solving, this specific case, then as Krystian mentioned, then you need to focus on tests and focus on making real tests. For example, it wasn't clear for me. Maybe it's because, as Theo said, I'm from image processing, not so much from machine learning and visual computing. What do you mean by camera normalization? Right? Yeah, asking exactly what did you do with the samples? What did you mean by camera normalization?
So our network is a feature extractor from the image. So for every input image, we generate an output vector. That's I think 128 dimensions with floating points like inside -1 and 1 values. So after we train our network, we apply them in all the images from the target domain, and we have a bunch of feature vectors from all the images of the target domain. Then we group the features by camera. So all the features for camera 1 is here, all for camera 2 here, and we separate them. Then we calculate the average vector. What is the average value for each dimension in these features from this camera? So we have an average vector of 128 dimensions too.
Okay.
And also a standard deviation vector, and we apply it for each feature.
Okay, so I see. So it's data normalization, which
yes.
But that makes a lot of difference. Krystian is right. Using data normalization from architecture and not using from another, it makes a difference, right?
Yes.
And also, and it's again, when you say baseline, right? I'm comparing to the baseline. It's hard to actually call it a baseline, right? When you have a training method, right? Because
sure,
it's not really the best you can do, right?
Yes.
Right. So that's what I think. Sometimes the thesis as a thesis, as a story, sometimes it leaks, right? So it doesn't seem you are sure what problem you are trying to solve, right? And I think Krystian already make a lot of points, so I don't want to go through it, all of them. But that's my contribution. If you guys are trying to solve a more generic problem, I think you kind of need to stop and go through the math, go through the modeling of the system, right? And if you guys are trying to work on a specific problem, then you have to set up limit conditions, right? So this is our limit conditions. This is what we are trying to solve, right? Right. I think you guys are trying to do too much.
Yes.
That's my main contribution, right? I don't think I will normally argue certain points, but like I said, I am satisfied with the work you have done for what I expect for a master's student, right? So that's the contribution I can give.
Thank you very much.
Oh, I was expecting a severe beat. Anyway, yeah, thanks, Bruno. Bruno, like he said himself, he's from the image processing background, and which means signal processing or engineering. And indeed, I think this is there's some analysis in the text. They're not, not as good as they could be. I think that's something that
but it's normal. I actually, there there are things that I learned for reading the text.
Okay.
Right? And there's a lot of things
was
that I
not a
learned
complete waste of your time.
for Krystian's comments as well. Right?
Great.
So,
But yeah, I agree. The camera-based normalization is really not explained very well in a formal way, like in terms of like telling what is actually taken into account when you normalize, and where you do it. Like, I mean, you could be doing it in the input of the network, actually, actually as a pre-processing step. You could, yeah, or you could do it in several layers of the network, and it's not actually that clear.
yeah, because in your first, when we say camera view normalization, basically is an affine transform. That's what we do.
Yeah. So it's not. I mean, it's just a basic statistical renormalization strategy, right? And yeah, like since you mentioned viewpoint, and Krystian also mentioned the viewpoint bias, which he's right, and it's an interesting point, important point. But I'm not. It was at least for me. I don't know if it was for Tiago, but for me, it's not completely clear what we should do in terms of experiments or the text, to address this viewpoint bias. Krystian, I don't know. Do can you give details or?
Go to the pose bias.
Yeah, pose bias. Yes.
I mean, it does exist, and people are aware of it. And there are techniques that sort of use some sort of adversarial training to reduce the influence of the pose. So where initially, for example, HK3 was designed such that the gallery was constructed only from cameras that have decent pose. And you ignore in the evaluation the same pose, but you can't just say that, okay, I will have no camera with the same pose ever. I mean, that's ridiculous, right? So that was wrong. And then in the other techniques, in the other data sets where you have a similar pose, right, you have the problem that all similar poses, different IDs are coming up before the actual correct ID, but different pose. So this happens a lot, and I mean there is. I think we measured that it was like on the level of 20%. I think if they did it correctly.
Okay.
That's quite significant bias. And there are other things like the poses. I think that there might be some sort of occlusions as well. Background obviously is quite strong, but background I think people deal with okay because there is enough variation from different cameras. Poses, you have more or less like 5 maybe poses, and and they affect a lot. So
So I have a kind of a question. Why using video would be more useful? Why just images, right? Because walking is biometric, right? Right.
It's different. I will just answer. It's a bit different task. So where complexity-wise, it's easier. There are people that do videos. There are data sets that have videos. There are data sets that have night time versus daytime recognition. So there are, but I think in the biggest sort of a general person re-ID, these data sets are considered as benchmarks, and most people are using them. So yeah, it's not that we don't do videos at all. No, I think it is. It's just that the way they are processed, we run people detectors, and then we assume that we have one frame and we retrieve. If we have more frames, then we can expect better performance. Okay, so that's typical.
Okay.
I think Tiago actually started from video, right?
No.
No. Okay. I mean, at least I know, like from the. So this work, I mean, this is not actually what he's doing at the moment in the company, but when he started working in this company, the work was triggered by, like, at least the research question, right, or the problem was triggered by a real application where you actually have surveillance cameras, and the surveillance cameras, they are capturing all the time, right? So in practice, you actually get videos. Like, Bruno is completely correct in that sense, but I don't think you actually tried to use, like, I think the best you did was something like a combination of a series of predictions. I don't know.
Sure. I'm sorry. I forgot this, but I have video and I have multiple examples of people. Inside the same camera view, I use tracking to help me with the features, and then I used some kind of statistics, like in the camera 1, if I saw the person 10 times, 12 times, I generated an average vector for this person from all the 10, 20 vectors I extracted. But I never tried to use some techniques that are for videos. I don't know, maybe something with an LSTM or RNN. I haven't tried that.
Yeah. But Krystian is right. I mean, when you have video, you have more information, and Bruno is also right that walking is a biometric. But when it comes to actually evaluating the work and trying to, write it in as part of a research paper, we come to that point that, at least when he started, back then I was not aware of enough person with ID data sets with actual video sequences. If they were they had very few samples. And if you look at person with ID literature, I think most of the papers are actually on with static images. But I bet Krystian knows more about that anyway. So yeah. Yeah. Okay. I guess I don't know. Well, let's see. We still have public outside the examiners. There's only all 2 people, basically. The others are gone. So anyway, do you guys have any question or want to comment? Maybe not. Oh, they're just quiet. Yeah. Well, if that's the case, so since we don't know how to do this with Teams.
This way is ask everybody to leave.
To leave, right?
And
I'll stop recording anyway. Well, thank you all for attending. It was very nice to have you here. But I will ask you guys, not Krystian, Mikolajczyk, or Bruno, but everyone else to leave, and then at some point we invite Tiago back to this thing.
And everybody else as well, if Tiago wants to come.
Yeah. Okay, and I stopped recording now, I believe. So, all right, so I see you guys later.